calculate the effective atomic number in the of the central metal atom in the given complexes. So in this question we have the different complexes, okay, and we need to find out the effective atomic number. So uh, first of all we need to understand that what is the concept, okay, what is the concept of EAN, okay, effective atomic number. So in the coordination chemistry, effective atomic number is given by Mr. Siswick, and he said that if any complex, okay, if any complex is following the EAN, which is equivalent to the noble gas configuration, then that complex will be stable. It means that uh, if you have any kind of the complex, right? So you know that in the complex we have the central metal atom, and there will be some ligands with some coordination numbers, okay, with some coordination number, okay. So in this coordination compound, we need to find out that what is the effective atomic number of this central metal atom or ion. Once you will understand what is the EAN, then you need to compare that the EAN is equivalent to noble gas configuration or not, okay, noble gas configuration or not. If this is equal to noble gas configuration, then you will say that the complex is stable. Complex is stable. And if it is not following the noble gas configuration, then you will say complex is not stable. Okay, complex is not stable. Okay, so this effective atomic number, it's a good tool to understand, to differentiate that which complexes are stable and which are not stable, okay. So this effective atomic number also have some limitations, and those limitations we will understand. But before that, we will talk about the EAN with the noble gas configuration, okay. What do you mean by the noble gas configuration? Noble gas configuration, simple meaning that you know that what is the noble gas configuration, okay. So in the noble gas configuration, you know that these helium, neon, argon, krypton, all right, xenon, radon, okay. So whenever we talk about that kind of the thing, then you need to understand that if this kind of the electronic configuration is achieved, for example, neon 10, argon 18, okay, then krypton is 36, right, then radon is the 86, all right. So if this kind of the thing you are getting, then you can say that this is your noble gas configuration, okay. So let's see that how to recognize the things, okay. Okay, so let's see. The first question, we have the copper, okay. So this is our copper complex, copper ammonium complex. So once you will do the ionization of this particular ionization sphere, so this will be your copper tetraamine NH3 whole 4, right? So that will be your plus sulfate 2 negative, okay. So definitely this will have some positive charge, so you can say that this coordination is sphere, okay. This coordination sphere is our cationic species, okay. So definitely the copper oxidation state of copper in this complex is +2, okay. So the oxidation state is +2, right. Now let me introduce the formula of the EAN, okay. So the formula of the effective atomic number formula, this is the EAN equals to number of electrons in the metal ion, okay, number of electrons in metal ion plus number of electron in metal ion plus number of electrons donated by ligands, okay, number of electrons gained from ligands, okay, gained from ligands. It means that how many electrons the metal ion is gaining from the ligands, okay. So some Werner's theory idea you required here, okay. So how the metal will receive the electrons from the ligand, okay, that kind of the thing we need to understand here. So if you talk about in this particular complex, so what is the EAN for this? So EAN will be how many number of the what is the number of electron in the metal ion? Okay, so copper, you know that copper is 29, okay, atomic number is of copper is 29, okay, but you know that the copper is present in the +2 oxidation state. It means it is losing its 2 electrons, okay. So 28 minus 2 plus how many number of electrons that it is gaining from the ligand, okay. So copper, basically the copper is gaining how many electrons, okay. So you will write that the one ammonia will give you the 2 electrons, okay. So this 4 into 2, okay, 4 different ammonium ligand, they will give the 8 electrons, okay. So that's how we solve the question. So this will be the 27 plus 4 to the 8, okay. So this will be your 35. All right, so this is your effective atomic number is 35. EAN for this first question is 35, right? Now let's move to the second question. So here we also have the coordination, ionization sphere. And if you just do the ionization, so you will see that this is the cobalt complex, okay. So you can write it here like cobalt hexamethyl, okay, and 3Cl negative. So definitely this will have the 3 plus charge, okay. So cobalt is present in +3 oxidation state. Once you identified that cobalt is present in +3 oxidation state, so now you can calculate the effective atomic number, okay, effective atomic number. So the effective atomic number is what? How many electrons in the ligand, okay, sorry, in the metal ion. So we have the cobalt, and you know that the cobalt having the 27 electrons, okay, because its atomic number is 27, so it can have the 27 electrons. But since it is present in +3 oxidation state, so we will subtract 3 from there, okay, right, because it is losing the 3 electrons, okay. So plus how many electrons are gained from the ligands? So we have the 6 methyl groups, okay, 6 methyl group, and one methyl group will give you the 2 electrons, so 6 will give you the 6 times 2, okay. So you need to understand that how many electrons the methyl group will give, okay. So here this is the 2, right. So 27 minus 3 is 24, okay, plus 6 to the 12, right. So this will be your 36. Now this is very interesting that the effective atomic number for this particular complex is 36. Now this 36 number, you know that this is the equivalent to the xenon, okay. That sorry, this will be the krypton, right. This will be your krypton, okay. So this is equivalent to the krypton, right. You can see here, okay. So that's how we do the effective atomic number calculation. So if you go with the next question, that is this one. So this is your potassium, okay. That's your potassium complex, so potassium with the mercury, Okay, so mercury complex. So do the ionization. So this will be your 2 positive plus Hg I4 negative, 2 negative, right? So this kind of the thing. So you will say that mercury is present in +2 oxidation state here. Okay, so mercury is present in +2 oxidation state. Now calculate the effective atomic number. So you know that what is the mercury. Okay, what is the atomic number, how many electrons the mercury can have? It is the 80, right? Okay, so 80 minus how many electrons it is donating? It is donating the 2 electrons, right? So 80 minus 2. Okay, then how many electrons it is gaining from the ligand? So ligand, we have the 4 iodine. Okay, so that will be your 4, and 1 iodine will give you the 2 electrons, right? 1 iodine will give you the 2 electrons. Okay, so this will be your 80 minus 2 is your 78 plus 4 to the 8. So this will be your 86, and 86, you know that 86 is nothing but it is the electronic configuration of radon, right? So now you can say that it is also a stable complex. Okay, this is the stable complex, you can say. Why? Because its electronic configuration is equivalent to the inert gas, that is the noble gas. Here we Krypton in the second B question, you can say that this is the stable complex, right? Now let's move to the solution of the question number D. So we have the silver ammonium complex. Okay, so let's do the ionization. Silver diamine, all right, and then this is your Cl negative, this is your positive charge. Okay, so we basically the coordination sphere is the cationic species. Okay, the positive charge species. So what you can calculate here is, you can say that silver is present in +1 oxidation state. Okay, so the effective atomic number. So how many electrons the silver can give? So silver, you know that it is having the 47, right? Silver can have the 47 electrons, but it is donating 1 electron. So that's why 47 minus 1 plus how many electrons it is gaining from the ligands? So 2 amine. Okay, so 2 multiplied by 2. All right. So this will be your 47 minus 1, 46 plus 4. Okay, so this will be your 50, right? This will be your 50. So this is not equals to the noble gas configuration. So you can say that, you can comment that this is not a very stable complex. Okay. All right. Now let's see the next question. The effective atomic number of the chromium in the given complex chromium hexacarbonyl system. Okay, chromium hexacarbonyl system, right? So let's see. So what we can do is just say what is the chromium. So this is your, if what is the complex? Chromium Cu6. All right. So we will write the chromium. Okay. So what is the effective atomic number for this is, okay, what is the effective atomic number for this chromium? So chromium, you can say that what is the electronic configuration of chromium? That is the chromium is 24, right? Scandium, titanium, vanadium, and chromium. Okay, so it is 24, right? So the metal ion will have the 24 electrons, right? Okay, so but let's see the complex chromium, and this is your hexacarbonyl system. Okay, so this will be your 24. Okay, 24 plus there are the 6 ligands, and these 6 ligands, the carbonyl will give how many electrons? The carbonyl will give it should be the 2. Okay, so that will be your 24 plus 6 to the 12, right? So this will be your 36. This will be your 36, and this 36, you know that this is the equivalent to the noble gas configuration. All right, noble gas configuration, that is the krypton. Okay, that is the krypton. So you can say that is it is the answer is 36, and the complex, this complex is very stable. Okay, you can say this is the very stable complex. Okay, because it is gaining the electronic effective atomic number of the noble gas. Okay, so that's how we solve this question. And now let's move to the next question. According to the rule of the effective atomic number, central atom acquires. So you what the central atom require according to the EAN? It is the option A is the inert gas configuration, B is the duplet, and C is the pseudo inert electronic configuration, and D is quartet. Okay, so we studied here that with the EAN, effective atomic number, we talk the complexes about their uh, inert gas configuration. Okay, we compare the EAN with the inert gas configuration. Okay, if it is following the, if EAN is equivalent to inert gas configuration, then it is very stable. Okay, now let's see the final question. So effective atomic number of the iron in this particular complex, right? So we have this particular complex, that is the K4Fe hexacyano system. Okay, hexacyano system. So if you do the ionization, so 4K positive, and this will be your iron hexacyano, right? This will be your 4 negative systems. Okay, so iron, you can say this is your, what is the oxidation state of this iron? Okay, if you use the oxidation state of this iron, okay, so we have this oxidation state of iron. Okay, how to calculate? You know that x plus 6 times minus 1 equals to minus 4. Okay, so x minus 6 equals to minus 4, and x will be minus 4 plus 6, that will be a plus 2. Okay, so here you can say that iron is basically present in plus 2 oxidation state. So what is the effective atomic number? Effective atomic number, the how many electrons the central metal atom have. Iron is having the 26, but it is losing the 2 electrons, so 26 minus 2 plus how many electrons it is gaining from the ligand? Okay, 6. Okay, so the question is that what is the cyanide? Okay, how many electrons the cyanide will give? So it is minus 1. So this is important. This is important that you should have the idea that the cyanide will give the minus 1. Okay, so this is your 24 minus 6. All right, so this will be your 18 electron. Just a minute. Okay, that will be your there can be some mistakes here because options of this question, I can give the options. Okay, so just a minute, let me check it out. What are the different options for this question? Yeah, so in this complex, there is some slightly changes. Okay, because the cyanide, okay, the nitrogen will give the 2 electrons, right? So there is a lone pair of the nitrogen which is present in the cyanide. So 6 2s are 12. Okay, so we will write here the 12, and that's how this complex will basically, this complex will get the 36. Okay, so this will be your 6 2s are 12. So okay, so that's how we will let me write it again, some changes here, right? Some changes. Okay, so I will write here the things again. Let's see. All right, so this will be your So this will be your 2. Okay, so 26 minus 2, that will be 24, plus 6 to the 12. So this will become the 36. Okay, so 36, which is again equivalent to the krypton, right? So that's how you can say that it is highly stable complex. Okay, it is also stability is high. Okay, stable complex, you can say. All right, so that's how we solve this question, and the overall idea of the effective atomic number, right? Thank you.